Welcome back, everybody, for another deep dive. This time, we're going to be tackling something called primitive permutation groups.
Oh, those are fun.
Yeah, they're pretty cool. And before you know, your eyes glaze over and you're like, what is this?
Yeah,
I promise it's way more interesting than it sounds.
it is.
Yeah.
It's really cool.
So we've got some excerpts today from the Online Encyclopedia of Integer Sequences.
Ooh.
That's entry A000000, no years for those of you who are, hardcore OEIS fans.
Yeah, if you know, you know.
If you know, you know. That's right. And we've also got the Wikipedia page on primitive permutation groups.
That's a good one.
Yeah.
So that's a great place to start.
Yeah, it is a great place to start. And it's kind of like, like a mathematical mystery novel.
That's a good way to put it.
Yeah, where we're trying to uncover the secrets of these special groups.
Mm-hmm.
So to crack the case,
Hmm?
I guess we need to start with the basics. What exactly is a permutation group?
So a permutation group is, well, first you have to know what a permutation is. And that's just like, if you think about rearranging a deck of cards, so every time you shuffle a deck of cards, that's a permutation. So it's a specific way of reordering things.
Okay.
And a permutation group is just a set of permutations that follow specific rules.
Okay, so like maybe their rule is they can only swap like 2 cards at a time or something.
Exactly. Yeah, so the rules determine which permutations are allowed in the group.
Okay.
And then within permutation groups, you have some that are called transitive, and that means no matter what order your deck of cards is in,
Right.
there is a set of permutations that are allowed in that group that can get you back to the original order or any other order.
Oh, okay.
So every single arrangement of the deck of cards
Right.
can be obtained by another one using the shuffles that are allowed in that group.
So it's like no matter how messed up the deck is, if our group is transitive, there's the sequence of legal shuffles that can get it back in order.
Exactly.
Okay.
Now, primitive permutation groups are a little bit more specific.
Sure.
So they are transitive, but they also don't preserve any non-trivial partitions of the set.
Hold on, partitions. Is this where things start getting messy?
It can be a little messy, but think about it this way. You're dividing a pizza into slices.
Okay.
Okay, so each slice of pizza represents a subset
Oh,
of our set of objects. So in this case, the cards.
Okay.
So a primitive group's shuffles would totally scramble those slices. Like you wouldn't be able to tell where one slice ended and another began.
Ah, I see. So like those fancy pizza places that cut the pizza in like weird asymmetrical shapes.
Exactly, yeah.
Okay.
With an imprimitive group, on the other hand, the slices would stay intact even if like their positions change.
Okay.
So you're just swapping 2 slices without cutting them up further.
Gotcha. So like you're saying, the Wikipedia article gives the example of the symmetric group S4 acting on the set 1, 2, 3, 4.
Right.
And it preserves the partition 1, 3, and 2, 4.
Yeah, so you can cycle those numbers all you want, but you're always going to have 1 and 3 together and 2 and 4 together.
Okay, those pairings remain unbroken. Okay, so we've got our pizza slicing analogy to understand the difference between primitive and imprimitive groups. But why should we care about this distinction? What makes primitive groups so special?
Well, one of the reasons that they're so fascinating is because of a theorem by this really brilliant mathematician named Évariste Galois,
Okay.
who unfortunately died very young, but he was a brilliant guy. He actually introduced the term primitive in his last letter before he died.
Wow, talk about dramatic.
I know, right?
So what did his theorem say?
So Galois' theorem states that if a solvable group
Okay.
acts primitively on a set,
Mm-hmm.
the size of that set must be a power of a prime number.
Okay, solvable group. That sounds like a whole other mystery we need to solve.
Yeah, so a solvable group is a group that can be broken down into simpler pieces in a certain way.
Okay.
But what's amazing about Galois' theorem is that it tells us something about primitive groups.
Okay.
So if we can prove a group is solvable and it's acting primitively,
Mhm.
we know that the size of the set that it's acting on has to be a power of a prime number.
So it's like a mathematical constraint on these pizza slicing groups.
Exactly. And what's really cool is that we can use this theorem to prove that certain groups can't be solvable.
Ooh.
So, for example, let's look at the symmetric group of degree 5.
Okay.
So that's like all the different ways to rearrange 5 objects.
Right.
The order of that group is 5 factorial, which is 120.
Okay. So 120 is a pretty big number. How does that relate to Galois' theorem?
So if that group were solvable and it was acting primitively on a set,
Uh-huh.
the size of that set would have to be a power of a prime number.
Okay.
And a 120 is not a power of a prime number.
It's not.
The prime factorization is 2 times 2 times 2 times 3 times 5.
Right. So it's got multiple different primes in it.
Exactly.
So it can't be expressed as a single prime number raised to a power.
Right.
Which means, thanks to Galois' theorem, that the symmetric group of degree 5 can't be solvable.
Exactly. That's the power of this theorem, is that it lets us rule out possibilities and like really understand the structure of groups.
Wow. I'm starting to see why these primitive permutation groups are causing such a stir in the math world.
Yeah.
It's amazing how this seemingly simple concept, like rearranging things, can lead to these like profound insights.
Yeah.
But I am curious about that OEIS sequence you mentioned earlier.
Yeah.
What does that tell us about these groups?
So that's where things get really interesting.
Okay.
The OEIS sequence A000000 length, it lists the number of primitive permutation groups for each degree.
Oh.
And it reveals some fascinating patterns and some unexpected jumps.
Ooh, I love patterns. So let's explore those in the next part of our deep dive. Stay tuned, folks, because things are about to get really wild.
I can't wait.
All right, so we're back and ready to delve into that OEIS sequence. A000000 is on it for those keeping score at home.
Mm-hmm.
You said that this sequence lists the number of primitive permutation groups for each degree.
Right.
What does that actually look like?
Okay, so picture a chart where each row represents a degree. So that just means the size of the set that we're rearranging. So degree 2 would be like rearranging 2 coins.
Okay.
Degree 3 would be like shuffling 3 cards.
Right.
So on. And then for each row, we just write down how many different primitive permutation groups there are for that degree.
So it's kind of like a catalog of all the unique ways to do that fancy pizza slicing
Exactly.
we were talking about earlier for different numbers of slices.
Exactly.
Okay. And so what does this list actually look like? What are the numbers?
So for the first few degrees, the numbers are pretty small and they seem almost random. So like degree 2 has 1 primitive permutation group.
Okay.
Degree 3 has 2.
Okay.
Degree 4 also has 2.
Oh.
Then it jumps to 5 for degree 5.
Okay, so not exactly a clear pattern emerging yet.
No, not yet. But then...
But you mentioned some unexpected jumps.
Yeah. So when we get to degree 16,
Okay.
the number of primitive permutation groups jumps to 22.
Whoa, 22. That's a huge leap.
Right.
Why 16? What's so special about 16 that there's suddenly so many ways to like primitively rearrange things?
So it turns out that a lot of these groups are hiding within something called the affine group.
Okay.
In 4-dimensional space.
4-dimensional space.
Over a field with 2 elements.
Okay, I think we need to like slow down for a second here.
Sure.
4-dimensional space. That sounds like something straight out of like science fiction.
Yeah.
And then what's this about a field with 2 elements?
I'm getting flashbacks to high school math class.
Right.
I'm a little lost.
Okay, so think about it this way. You're used to thinking about representing points on a line,
Right.
which is 1-dimensional space, or on a plane,
Mm-hmm.
which is 2-dimensional space.
Right.
4-dimensional space is just an extension of that concept,
Okay.
even though it's hard to visualize.
Yeah.
But you can do it mathematically.
Okay, so like if our coins or cards or whatever were actually like floating around in this 4-dimensional space.
The affine group would be like all the ways we could move them around while keeping certain relationships intact.
Exactly. It's like our transitive groups.
Okay.
But in a much more complicated space.
Okay.
And the field with 2 elements just means that we're working with a very basic number system where we only have 0 and 1.
Okay.
And it might seem strange,
Yeah.
but these things called finite fields are really important in math and also in computer science.
Okay, so we've got these primitive permutation groups like hiding out in 4-dimensional space,
Uh-huh.
which is already pretty mind-blowing.
Yeah.
What's the connection back to our OEIS sequence?
So the fact that so many of these degree 16 groups are subgroups of this affine group
Uh-huh.
explains why there's a sudden jump in the sequence.
Okay.
It's like we stumbled upon this hidden treasure trove of primitive permutation groups,
Okay.
all within this larger structure.
So it's not just random chance that there are 22 of them at degree 16.
No.
There's like a deeper mathematical reason behind it.
Yeah, a much deeper reason.
Okay, cool. And as we go further down this OEIS sequence, do we just keep finding like more and more crazy stuff?
Yeah, so as you go further down, you find even more intriguing patterns and connections to other areas of math.
Wow.
So it really highlights how vast and interconnected this whole world of primitive permutation groups is.
It's incredible to think that this simple idea of like rearranging things can lead to such like deep and complex mathematical structures.
I know.
But what about the rest of the sequence? Like, does it just keep going on forever?
So the OEIS entry only lists terms up to degree 4095.
Okay.
But that doesn't mean that they stop there. Mathematicians are still discovering new primitive permutation groups all the time.
Oh, wow.
Pushing the boundaries of what we know.
So it's like an ongoing mathematical exploration. We're just scratching the surface of like understanding these groups
Yeah, exactly.
and their connections to other areas of math.
Yeah.
Well, now I think it's time to step back and think about the bigger picture. Like, Why should anyone care about these things?
Right, that's a good question.
All right, so we've explored what primitive permutation groups are. We've seen how Galois theorem helps us understand them. We've even glimpsed this vast landscape of the OEIS sequence.
Hmm.
But I have to ask, why does any of this matter?
Yeah, that's the question.
Yeah, is it just like a mathematical curiosity? Or are there actual real world implications to these pizza slicing card shuffling groups?
Right. So it's both.
All right.
On the one hand, they're incredibly fascinating just in their own right.
Mhm.
They reveal these deep truths about symmetry and structure that
Yeah.
have captivated mathematicians for centuries.
Right.
But their influence extends far beyond pure math.
Ooh, intrigue. Give me some examples where these groups pop up in the real world.
Okay, so for example, cryptography.
Okay.
So secure communication relies on these complex mathematical algorithms.
Right.
And primitive permutation groups play a role in designing and analyzing those algorithms.
Mm.
So their properties help ensure that messages can be scrambled and unscrambled reliably,
Yep.
keeping sensitive information safe.
So the next time I send a secret message on a very secure messaging app, I can thank primitive permutation groups for keeping my secrets safe.
Exactly.
That's pretty cool.
And it doesn't stop there. Remember how we talked about finite fields with two elements?
Yeah.
So those are actually the foundation of modern computing.
Okay.
So every bit in your computer is a 0 or a 1.
Right.
And understanding how things behave in those fields is crucial for designing efficient algorithms and building reliable hardware.
So these primitive permutation groups are kind of like the hidden gears behind our digital world.
It's true.
That's crazy. I never would have guessed.
Yeah, and let's not forget about physics.
Okay.
So symmetry is this fundamental concept in the universe.
Really?
And these groups help us understand how particles interact
Okay.
and how forces operate.
Mm-hmm.
They even play a role in string theory, which attempts to unify all the forces of nature.
Whoa. So we've gone from pizza slices to the fabric of reality.
I know, it's pretty wild.
That's a pretty impressive journey.
And it's not over yet.
Oh,
There are tons of areas where these groups have potential applications, from designing better materials to optimizing complex systems.
wow.
So we're still uncovering new connections and possibilities.
It's mind-blowing to think that something as seemingly abstract as rearranging objects can have such a profound impact on our understanding of the world
Yeah,
and even the technologies that we use every single day.
it is pretty cool.
That's the beauty of math, isn't it?
It is.
It's this language that unlocks these hidden patterns and reveals these connections we never would have imagined.
Totally.
Oh, I think we've successfully cracked the case of the primitive permutation groups.
I think so.
We've explored their definition, their connection to Galois' remarkable theorem, and even their surprising real-world applications.
Mm-hmm. It's been a pleasure talking about this with you.
Likewise, and to all our listeners out there, thank you for joining us on this deep dive into the world of primitive permutation groups. Hopefully you're now as captivated by them as we are. Who knows? Maybe one of you will be inspired to make the next big breakthrough in this field.
Yeah, that would be awesome.
Until next time, keep exploring, keep asking questions, and remember, the world is full of mathematical wonders just waiting to be discovered.